All right, let's talk about the periodic table now and give you a little bit of history, a little bit of perspective on how this was created and some of the information that it provides. And you've already seen a good bit of that between looking at the electron configurations and some of the other things that we've done. But let's talk about the periodic table. And so here's some things that we're gonna cover. All right, we'll talk about its arrangement by protons, the group of elements, three broad classes, and some of the main group elements. So a little bit of background on it. By 1700, we'd only discovered really a handful of elements, and most of them things that we could commonly use. But then there seemed to be a bit of an explosion in science, and we found ourselves discovering just a plethora of elements, and we needed some way to arrange them, some sort of categorization. Um, and so the first one that came up was by this guy J.W. Dobereiner. He came up with the triad theory, which really just tried to group up elements that had common properties into groups of three and sometimes more. But really, the problem became that not only did not all the elements fit into these triads, but then you had to memorize all these different triads, and you kept coming back to again this disorganization. So he started though with this idea that certain elements have similar properties and can be grouped up. And so in 1869, this guy Dmitry Mendeleev comes along, and he needs a way to explain it to his students. He's a professor. He needs to come up with this design to be able to categorize it. And so at this time, a lot of people are trying to make a table of elements or some sort of organization system. But let's take a second to just think about what did the atom look like in 1869. So we learned about Dalton and Thomson and Rutherford and Bohr, but in 1869, it's prior to Thomson, Rutherford, or Bohr. So at this point, we didn't know that electrons existed. We didn't know protons existed. We didn't know there was a nucleus. We only were going off of the Dalton theory, which is that atoms are these solid objects. And so we didn't have all the different things like atomic number and number of protons, number of electrons, number of neutrons. We had atomic mass. And so Mendeleev arranged it by increasing atomic mass. And this is first periodic table. And so what we can see here is that it's kind of similar to the arrangement in ours, right? Boron, carbon, nitrogen, oxygen, fluorine. Okay, a little bit different. Then you get some groupings here. Lithium is above sodium, which is above potassium. All right. You start to see, fluorine, chlorine, bromine, iodine, all in a row. And so this is what he did. He was able to group them up based on these repeating properties. So he grouped them by mass, but then also by properties. And with doing this, what would happen is he was able to predict that certain elements would exist. So we had, zinc here, but then some of the properties didn't show. So, okay, well, we didn't have a property that was like aluminum. We didn't have a property like silicone. And then we got into it again. So he left these spots with question marks saying, we will discover elements that fit here. They're probably going to have a mass right around these numbers. Okay, not only was he able to do that, but down here with tellurium and iodine, it turns out that iodine had a mass of 127, tellurium had a mass of 128, but the properties didn't fit to have them there. The properties fit to have iodine with bromine, chlorine, and fluorine, how it is on the periodic table now, and have tellurium with its group. And so what he did was he put this question mark there saying, well, something must have gone wrong with the mass of tellurium. It must be incorrect. But it turns out it wasn't incorrect, right? It was indeed correct. And the reason is that in 1913, Henry Moseley discovers the atomic number for every element, and now we arrange it by atomic number, the number of protons. And so our current periodic table is number of protons, not the mass. And when Mendeleev had this periodic table here with his arrangement, he was able to predict that. And these predictions are what really set his model aside. This is what gave him the credit for the periodic table, because there are some that have been developed over the years in this same time period that were very, very close. And they had even similar arrangements, similar looks, but he was kind of the only one that was able to predict the existence of future elements or predict the inaccuracies in our current knowledge. Okay, and so again, after Rutherford discovers the nucleus, Henry Moseley discovers the atomic number for every element, and now we know the periodic table is arranged by atomic number. And so what we have here is groups and periods. So a group is up and down, right? Group 1, group 2, group 7, group 8, and those things are going to have similar properties. So all of the group 1 elements are going to have similar properties. All the group 2 elements are going to have similar properties. We've seen that in a few of our labs. We've seen it in a few of our demos. We've definitely seen it when we talked about electron configuration, that we have the repetition, right? And then the periods are left to right, okay? They're those rows, and essentially they're a repetition of the properties that we see in each group. All right, so we come up with this periodic law, which states when elements are arranged in order of increasing atomic number, there's a periodic repetition of their physical and chemical properties. So what does that mean? Well, it means that when we put them in order, if we were to stand them side by side, 1 to 118, every so often we hit a similar property. And so we saw in one of our demos the reactivity of alkali metals with water, right? And so that group 1, we saw lithium with water, sodium with water, potassium with water. And if you continue, you see that. So if you were to line up these elements and you were to hose them down with some water, every so often that element would react violently with water, and that's group 1. And so that's a periodic repetition, right? You go by and you say, oh, lithium reacts violently with water. Well, beryllium doesn't, and boron doesn't, and carbon doesn't, and nitrogen doesn't, and oxygen doesn't, and fluorine doesn't, and neon doesn't. And then you get the sodium, spray it down water, and all of a sudden there it is, it reacts violent. Oh, well, let's put that thing in group 1 because it goes with lithium. They are the alkali metals. Okay? And so this is our general broad periodic table. You know that. We kind of cut out that F section and put it underneath for space. All right. And this brings us into our next division, which is the 3 classes of elements. Okay. We have metals, nonmetals, and metalloids. And I wanted to just quickly shoot back so we can get a periodic table to look at. But if we look here at our periodic table, see these dark green ones here, boron, silicon, germanium, arsenic, antimony, tellurium. These guys here are the metalloids, okay? And you can see they kind of act as a divider here, right along. This diagonal staircase, okay? Everything to the left of them is a metal. Everything to the right is a non-metal, okay? With exception to hydrogen. Hydrogen belongs here with the non-metals, all right? But everything else in here is metals. Everything up here is non-metals. And so let's look at some of the properties. Well, metals are good conductors of electric and heat. We know that. They're also solid at room temperature, except for one, which is mercury, all right, which we put in thermometers, in fire detectors, okay? And a big property of metals are they're both ductile and malleable, meaning that we can pull them into wires, we can stretch them into thin wires, right, cables, and malleable, we can pound those things into really thin sheets, we can bend them and they maintain their strength. Our nonmetals are going to be gases and solids at room temperature, except for one of them, which is bromine. All right, bromine is a liquid at room temperature. It's a red-looking liquid. And those are the only two, bromine and mercury, the only two elements in their pure elemental form that are liquid. And so the nonmetals, I put up there very prominent in nature because, well, we're mostly made of nonmetals. We're mostly made of carbon and water, right? Which is all nonmetals. Most of the stuff we interact with on the surface of the earth and the living world is nonmetals. Now, that's not saying that we don't have metals in us. We do. We need to consume metals to survive. It's just that by proportion, most of the stuff that we interact with in the natural world is going to be non-metal. And nonmetals tend to be poor conductors, and they're brittle. They crack instead of bending. That brings us to metalloids, which are that divider, right? That divider right down the periodic table. And these things, well, they share the properties with both metals and nonmetals. They kind of, depending on the environment they find themselves in, that's how they act. All right, silicone is a prime example. It can be an insulator when it is with other non-metals, but if you mix it with metals, it becomes a semiconductor. It tends to conduct electricity. All right, so it depends on what environment you put it in. All right, and so they can go either way, and that's that again. They're that divider on that portion of the periodic table that we saw. All right, and then the last thing defines just what we have. We have main group elements and transition metals. So the transition metals are those things in that D and the F series, really. They're the ones in between. The main group elements are what we refer to as 1 through 8. All right, so you can have group 1, group 2. We kind of skip over the transition metals to go 3, 4, 5, 6, 7, and 8. All right, and these transition metals have unique properties of which we are going to talk about. We already saw one when we did electron configurations, and we had that something like copper is an exception to the rule where it likes to have those electrons move into the d orbital before filling out the s orbital. And so these transition metals tend to have some unique properties, which we're going to see in the ensuing units.